Hello, everyone. This is Kalema Alan, and today we're talking about predicting chronic diseases using graph neural networks. I reviewed a paper called A Weighted Patient Network-Based Framework for Predicting Chronic Diseases Using Graph Neural Networks. This paper was written by Oli Lu and Hadat Woodin. It was published on 19th November 2021, and the keywords were chronic disease prediction, graph neural networks, hypertension, network, weighted patient network, and network patients. The link will be provided in the description below. Today we are going to look at the introduction, the computation problem of the paper of the article, the methods used, the machine learning models that were implemented, the model evaluation metrics that were applied, results of the discussions, strengths and weaknesses. So I'll start with the introduction. This paper is a 12-page paper that addresses coronary disease detection through the use of graph neural networks and weighted patient networks. The author of this paper so challenges in the traditional methods whereby they solely relied on the individual patient features and potentially missing the relationships between the patients. So what he decided to do was to implement the GNN to address this limitation. And the reason for its implementation was it excels at learning network structures and making them suitable for capturing hidden relationships between patients based on the shared diseases. This framework also employs a weighted patient network constructed from administrative data. And in this, there are weights, and these weights show the strength of connection between patients based on the shared disease diagnosis. The computation problem that was aimed to solve. First of all, the application domain for this whole research was chronic disease prediction within the healthcare sector. The computation problems that were aimed to solve by the author was predicting the risk of chronic diseases for individual patients. There was also extracting meaningful information from the healthcare data to identify the patterns and relationships associated with chronic diseases. The third one was to develop a computation model that can learn from the network structures of a patient to improve the prediction accuracy. The methods the author used in this research paper as follows. First of all, the data source where he got the data from was he identified administrative claim data for Commonwealth Bank Health Society in Australia, which was covering up to 1.24 million patients between 1995 and 2018. And the diseases that were covered in this research paper that we targeted, we have cardiovascular disease and chronic pulmonary disease. These are all heart diseases. And in this data that was claimed, they selected patients. There's a criteria that was used to select patients to be used, which was patients with at least 2 admissions, and then patients with relevant ICD codes for the targeted diseases, CVD or CB. ICD codes, yes, they are just the international codes for the different diseases. So they were looking for patients that had ICD codes for the targeted diseases, and then patients without the targeted diseases for the control group. And since we wanted to train a model, so they decided to come up with they decided to mix up people with and without the disease so that they can deal away with the bias in the system, and then applied outlier detection techniques. The features that were hinted on, they were age, gender, and smoking history, based on the ICD codes, of course. So also we had now the network construction. And remember, we're covering graph neural networks, which learns from the relationships between patients. So they had to create a network construction, which is also known as a weighted patient networks. And how they did this was by creating a bipartite graph showing patients' relations patient-disease relationships. I will show you how the bipartite graph works and how it was implemented. They also projected this was projected onto the patient side to create a WPN. And ages connect patients with shared diseases, and age weights represent the number of shared diseases. The models, like GNN models, we use in this research, there were two. There were graph convolution network models and graph attention network models. For convolution, they learn representation by aggregating information from the neighboring nodes. In other words, they collect information from the neighboring nodes, while graph attention networks, they are similar to GCN, but they use an attention mechanism to focus on the most relevant neighbor during passing. For learning, for training, for under prediction, they use the learned node embeddings, and for optimization, they use a binary cross entropy loss function, and for training, they are them optimizing. So the models applied in this research, they compare two main categories of machine learning models for chronic disease prediction. They first use the graph neural network based models, which was the GCN, and as I talked about earlier, and the DAT, graph attention network, which focuses on the most relevant neighbors, aggregating information, potentially leading to a better performance of this task. And the others were baseline models, as we know them. We have the logistic regression, support vector machine, and random forest. And they introduced a new one, artificial neural networks. And this one is a fully connected network within multiple layers. It learns complex relationships between features and the target variable through backpropagation, a technique for adjusting network weights. So, as I mentioned earlier, the process of creating a weighted patient network was they got the administrative data, as you can see in part A, data set, and they sampled it into two cohorts. Cohorts are like patients. In black, they are the ones with disease, and cohort 2 are ones without. So they created a bipartite graph. Here they were trying to connect the different diseases to the different people. In this scenario, they're aiming to predict a disease through connecting people with shared diseases. In other words, there are more than one diseases in this area where they're being connected. They are showing a connection between those diseases so that they can come up with patient network. And this patient network in part B was passed through a GNN model. For this case, we have two, and the GNN model will release an output, which was a 0 or 1, which shows that someone had a prediction, had a disease or not. But C just explains what I've just talked about in part A, and they also provided us with a pseudocode, which shows the different steps that were taken. Here we have the input, which is patient and disease, and the output is its prediction. And so for each patient, P1, 2 to 5, we are going to do a diagnosis. And if they are diagnosed with D, disease D, J, then they add the age and they create a bipartite graph with PI and J. And for each patient that is in the bipartite graph on the second part, if P1 and P2 have at least one disease in common, then you add the age between PI and P2. As if they share disease, you put them in an age, you add an age and you put it in an age list, but you also add a weight. Remember, weight is the number of common diseases between P1 and P2. And for part 3, each patient 1 to 5, if age list, then if for each patient 1 to 5 who are in the age list created above, if you put the patient PI with the age list in the GNN based model, and disease prediction will be put out as an output, sigmoid ZI. So this table shows the metrics that we applied, and the metrics we have were accuracy, precision, what, and F1. These other ones are true positive, true negative, and FN. But here, since we have network features, they divided this into two. We have an evaluation with network features and ones without. And the methods here are our modules that we applied. As we see, there are 1, 2, 3. There are 6 modules, but they were evaluated with network features and then without. So the results, please remember the experiment setup. We did 60% training, 20% validation, and 20% testing. And the baseline modules were given, as I mentioned, in modules were given. And to note, network features improve the baseline model performance. So the overall output was the EAT, or graphical attention, the EAT had the highest accuracy of 93.49 for CVD and 89.15. Remember, to do cardiovascular diseases were evaluated. Also, GAT had a high precision and a high recall and F1. Compared to other models, it had a high false positive than any other than a false negative, which is favorable for early disease detection. In other words, it's favorable to have a false positive than a false negative because it can help you to detect diseases in time. In other words, it can help to detect diseases in time. Also, GNN performance is similar with and without age weights, whereby the majority weight was 1. Age weights are simply the number of shared diseases between the diseases. So here this table shows the features, GNN models, and baseline. So here, learning patient representation, GNN models excelled in that, while in baseline models it wasn't as effective. Then important network features, we had the important network features. These features include the baseline model performance than it did with GNN models, performance accuracy, accuracy, precision, F1 score were high in GNN models, as we've seen earlier, and they were lower and for baseline models, they were slightly low, and false negatives and positives. These had a higher false positives, and which, as I said, is better for early prediction. And then impact on age weights. Performance drops without age weights, and performance improves without weights. In other words, in GNS, they rely on connection, and as if age weights are provided, the connection is the performance is at its peak. So under the strengths and weaknesses, GNN models effectively learn from the network. Then they capture information about a patient and the overall structure, leading to a better prediction. Then network features improve baseline models, as I mentioned earlier, and then they focus on early detection. This paper acknowledges false positives, identifying a healthy individual as at risk. It might occur, but it's important in catching the potential diseases early. For weaknesses, we have limited exploration of age weights. Although age weights were introduced in this paper, they didn't necessarily show us how to best utilize it, which was a problem. The difficulty to interpret. GNN models are complicated, and the paper does not necessarily show us how they understand and how they come up with the results. Data limitation. This study uses administrative data, which may have a limitation in accuracy and might not be generalizable to the population healthcare. In conclusion, this paper used the GNN models, and preferably GAT was the best at prediction and accuracy. While it needs improvement in acknowledgement of potential age weights, and also GNNs are complicated to interpret. And there is a room for improvement.